So now we'll be officially starting our unit on magnetic fields. And again, fields, if you think about it, is nothing new to us. Previously, we've talked about gravitational fields. We've also talked about electric fields. And we know that what is common about fields is that this is a region where some particle experiences a force. And then depending on the type of field we are talking about, the particle could be different. So for example, in gravitational fields, we say it's the mass which experiences the force. In electric fields, we said that this is where a charge experiences a force. So for a magnetic field, we say that this is a region where a magnetic pole experiences a force. So that magnetic particle which experiences a force is called a pole. So you guys probably already know that there are two types of poles. So there is the north pole of a magnet, which is called N, and similarly you have the south pole, which is called S. So how this is drawn is like this. So usually, again, for some reason, the north pole is always marked with a red sort of a color. This is the closest color I have to red. And then south poles are marked with blue. So again, this is fair enough. So again, the idea why we have two different types of magnetic particles here. So you have a north pole and a south pole is because if you have ever played with magnets before, you'll know that magnets can attract or repel. So in terms of the forces in terms of the poles are like this, that like poles, so basically similar poles. So basically if you have north-north or south-south, like poles repel and unlike poles, so north-south, and again if I say south-north it means the same thing, unlike poles attract. So the most important and also the very first example of magnetism that humans ever discovered was the use of a compass. And what a compass is made of is basically some magnetic material. The very earliest compasses were made of lodestone, which is basically an oxide of iron. And this, when put in, for example, a liquid, let's say in water, it would always come to rest in the same direction. So this gives us an idea that there is something here that makes it come towards the same direction all the time, irrespective of how it's released at some starting position. So wherever it starts from, it always comes to rest in the same directions. So this gave us an idea that the Earth in itself also has a magnetic field. And how we can understand this is as if we have a magnet which is inside of the Earth. So just ignore the lines for now. We'll also talk about what this is, and you guys might already also have some previous idea about it. So what happens is that this the magnet inside the Earth is like this, so that the north pole is at the bottom and the south pole is at the top. So when we have a compass, the way in which it settles is because since this is a south pole, it will attract the north pole of the compass. So a compass will settle in this direction, with this being the north, and similarly the north of the Earth will attract the south of the compass. So this is called the south pole of the Earth, but this is really in the northern hemisphere of the world, and similarly the north pole is in the southern hemisphere of the world. So what the magnetic south pole is the geographic north pole, and this is exactly why the This is how we define it, is because the compass points towards the geographic north, and similarly the north pole of the Earth's, so the magnetic north pole of the Earth is where the south point towards, and this is your geographical south pole. So just some basic common knowledge about compasses and the magnetic field of the Earth. So the red lines that we saw above are called the magnetic field lines. And what these do is that they show the direction of force which is acting on any magnetic material which is placed within the field. So again, because you have two types of particles here, the direction of force is defined by convention according to how it would act on north pole, right? Similar to how when we talked about electric field lines, so that showed how the direction of force would be on a positive charge. So here this is with respect to a north pole. So the rule for drawing magnetic field lines is that these field lines will start from the north pole and these will end at the south pole. So let me shift this here so we have all the rules for drawing the magnetic fields in one place. So these are sort of check boxes that you must tick off whenever drawing magnetic field lines. So before that, let's have a look at how we can actually visualize the magnetic field lines for a practical magnet. So there are two ways you can get the magnetic field lines. One is if you sprinkle iron filings on top of a piece of paper on which you have the bar magnet, and when you give it a nice little shake, you'll see these magnetic field lines coming into effect, right? So these dotted lines are how you get the magnetic field lines by the help of iron filings. Or what you can also do is use a plotting compass. So you start from some pole. Let's say if you even don't know what pole you're starting off with, by the way, you usually do know the poles. So let's say you start from any pole, you mark the position of the compass. So you place a dot at the starting point. So basically the north poles here. So you just have the north, 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 north throughout all the way from here to here. Because you know that this pole is the north pole, the tip of the compass is the north pole. So you just join the tips and this is how you get the magnetic field lines. So just you would need to do this over and over again at different distances to get the field lines. So the first thing that you need to remember is that the magnetic field lines start from the north and end at the south. And there's also a very easy way to remember this, that if you just remember it's the direction of force acting on a north pole. So what the field lines going like this, and there would actually be an arrow here, for example like this. What this shows is that if a north pole is placed here, so it would go in that direction. And that makes perfect sense to us because we know that north and north are like poles, so this one is going to repel that one. And similarly, south is an unlike pole, so this north pole would be attracted by this. So the first thing you need to take care of here is this requirement, that they start from the north and end at the south pole of the magnet. So the second requirement is just this, that since like any field, the magnetic field lines will also fall off with distance. So when you're drawing the field lines, we need to make sure that there is an increasing distance between the field lines. So what that means here is that as if you look at this, so the distance between both of these is something, but the distance between them is greater than this distance. And then this one should be greater than that distance even, and so on. So this is how you must make sure that the field lines are plotted. And apart from this, something which is very simple to see is that the field lines never cross each other, right? They're all separate lines which never intersect outside the magnet. So let's have a look at some common field patterns between different arrangements of the poles. So as we said above, and why the distance was increasing is because the magnetic field strength was basically reducing. So the spacing of the field lines, so how far apart the field lines are, indicate the magnetic field strength. So how strong that field is at that given point. So the less the spacing, the greater is the magnetic field strength. And again, let's see this using this much clearer diagram. Because of the dotted lines above, maybe it was not very clear to see, but let's have a look at a cleaner diagram now. So as we can see here, the field lines are much closer together, closest to the magnet. So this shows a very strong field strength nearby the magnet. But as we get further and further, so as you can see, this is some distance, but then this distance is even greater, and then that distance is even greater, and then this is greater still, which basically shows that the further the field lines are getting, the weaker is the magnetic field strength away from the magnet. And again, as we can see, the magnetic field lines are north to south. So some field lines are like this, and then others are coming into south, and this is how the field lines are between the poles. So now let's have a look at some common magnetic field patterns between different arrangements of the poles. So if we want to draw the field patterns between magnets which are placed like this, so that you have north and south poles which are closer to one another. So the idea still remains the same, that the field lines would go from north to south, and again where the distance between them is the least is where the spacing is also the least, showing the greatest magnetic field strength. So between the poles, right between this region, you can see that the field lines are almost parallel, which actually show that the magnetic field strength is almost constant here. So if the spacing remains constant more or less, then the magnetic field strength also remains constant. And then it starts to curve outside, and this is exactly like how we drew the magnetic field, the electric field patterns back in the chapter of electric charges and electric potentials. So this is how the field lines look, and then again the rest of the part remains the same, that north to south of the magnet itself, and then you have field lines coming into the south. And the same thing here, instead that this is the north, so here the field lines are from north to south, and since this is north, the field lines are going outwards from here. So in this one, if you have two north poles which are nearby to one another, so you know that for both of these north poles, the magnetic field lines will be heading out. But you also know that if you place a north pole here, then both of these north poles would be repelling this, right? So both of these are trying to push them away from one another. So here what's happening is that the north pole, which was previously drawn like this, and the north pole for this one, which would be drawn like this, they cancel out in some regions, and that gives you a neutral point right in the middle of both of these two magnets. So this is how the magnetic field patterns look like if you have two north poles which are close by to one another. All the other things remain the same, that from north poles the field lines are heading out. You have north to south lines and lines coming into the south, which is also the same here. If these were two south poles, then the only difference would be that now the field lines would be coming into and not going out of the poles. Otherwise, everything else remains the same.